Hello everyone, I am Kashish Patel and today I am thrilled to guide you through one of the most critical process in machine learning, which is model selection. In a world overflowing with algorithms, choosing the right model isn't just a technical decision, it's a strategic one. So, this presentation will explore key principles, practical techniques and examples to help you make confident and informed choice in your ML journey. So, let's begin with the importance of model selection. That why model selection matters. One of the biggest risks we face is overfitting. When a model memorizes noise in training data and fails in real scenarios. It's like a student who crams for an exam but forgets everything later. On the other hand, underfitting is when our model is too simple and doesn't capture the data's pattern. Imagine trying to fit a straight line in a curve, and even if a model performs well, it's too complex. It may not be feasible to deploy due to high computational cost. So, ultimately, the model we choose must balance accuracy, generalization, and efficiency. Now, let's move toward understand the bias-variance trade-off. So, basically, what is bias? A bias is an error due to overly simplistic assumptions, and you can take it as when we have high bias, it leads to underfitting. And talking about variance is the error from too much sensitivity to training data, and you can take it as when we have high variance, it leads to overfitting. So, a good model selection strikes a balance, low enough bias to learn patterns and low enough variance to avoid noise. Think of it as tuning a guitar, too tight or too loose, and the note is off. We want the sweet spot of balance. So, we must understand what is bias and variance trade-off. So now let's talk about resampling methods, which are cross-validation techniques. Cross-validation helps us evaluate models' reliability. Let's walk through a few key techniques. K-fold cross-validation. Here we are splitting the data into K parts. Train on K-1 and test on the remaining one. Repeat K times. Another one is stratified K-fold, like K-fold, but ensures each fold has the same class distribution. Very useful in imbalanced datasets. The third one is leave one out, which is also known as LOOCV. Each data point is tested once. This is super accurate but computationally expensive. The fourth one is time series CV. For this, the time dependent data is provided. This method maintains the order to avoid future data leaking into training. These techniques help reduce the risk to choosing a model that only performs well on a specific split. Now, let's talk about information criteria, in which we are going to talk about AIC and BIC. So, beyond accuracy, we also have information criteria to evaluate model quality. So, AIC estimates how much information is lost by a model. It balances fit and complexity. Whereas BIC, it is similar but penalizes complexity more strongly, favoring simple models. So, AIC is better when we care about prediction, while BIC is better when we are trying to uncover the true underlying model. Both are especially useful when comparing models that aren't nested or related. So now let's talk about what is regularization. Here we are going to talk about L1 and L2 penalties. So basically regularization is going to help us to avoid overfitting by discouraging overly complex models. So first of all we are going to talk about L1 regularization, which is also known as Lasso. It penalizes the absolute values of coefficient. It can shrink some of them to zeros, effectively performing feature selection. The another one is L2 regularization, which is also known as reach. It penalizes squared values of coefficient. It shrinks them but never zeros them out. The third one is elastic net. It combines both. It's powerful when we have many features, some of which are correlated or irrelevant. So basically regularization doesn't just reduce overfitting, it often leads to simpler and more interpretable models. So let's talk about performance metrics, that choosing how to choose the right evaluation. So choosing a performance matrix is just as important as choosing a model. So here accuracy works for balanced dataset but can be misleading when classes are imbalanced. Precision, recall and F1 score give deeper insights, especially when false positive and false negative are costly. ROC curve and AUC visualizes model performance across different thresholds. Higher AUC means better separation between classes. For regression, RMSE penalizes large errors, while MAE, which is nothing but mean absolute error, treats all errors equally. The takeaway: always aligns your evaluation matrix with the business objective. Now, I am going to provide a practical example. So, let's tie everything together with a real world example: predicting customer churn. So, step 1, we define the problem and identify data challenges like missing values or class imbalance. Step 2, we clean and pre-process the data. Step 3, we shortlist models, say logistic regression, random forest and gradient boosting. Step 4, we use stratified k-fold cross-validation and tune hyperparameter via grid search. And step 5, finally we evaluate the top models on the test set and choose the one the best balance, perform and practically. This is the essence of a thoughtful data driven model selection process. So talking about the conclusion, here I am going to discuss the best practice and future directions. So to wrap up, let's reflect on some best practices. Start with a deep understanding of problems and the data. Experiment bodily. Model selection is an iterative journey. Look beyond metrics. Consider model transparency, training cost, and deployment feasibility. And finally, remember ethics. We must ensure our models are fair and explainable, especially in sensitive domains. The future of model selection is not just about performance, it's about trust, responsibility, and a real world impact. Thank you.